Okay, so far all we've considered are electron groups that are bonded to atoms. Next we're going to take a look at the effect of lone pairs. Okay, so the first example will be ammonia. We've already discussed if we draw the Lewis structure of ammonia, we'll see that it has 3 hydrogens bonded to the nitrogen, and there's a pair of electrons to give nitrogen the octet, and we will call those lone pairs of electrons going forward. Okay, so if you think about the electron groups, whether they be a bonded electrons in a single, double, or triple bond, or lone pairs, we're going to count them as electron pairs. When we consider both of those types, what we're referring to is the electron geometry. So for ammonia, we have 4 electron groups. 3 of them happen to be bonded atoms. One of them is a lone pair of electrons, but those 4 electron groups create a tetrahedral geometry, just like methane did. Okay. When we just consider where the atoms are at in space, sort of leaving out the lone pairs for a little bit, what we get and what we refer to is the the molecular geometry. This gives us, for ammonia, leaving out the lone pair, gives us a trigonal pyramidal shape. Okay, you can think about this, 3 sides and then as pyramid, and the very important aspect of trigonal pyramidal as opposed to trigonal planar is that their atoms are not all in the same plane. Depending on how you look at it, you can think about these 2 nitrogens in the same plane, this one coming out at you, this one going behind you, or these 3 hydrogens would all sit on the table, and this one, the nitrogen, would be in a slightly higher plane. Very different from trigonal planar. Okay. If we take a look at water, we've drawn this Lewis structure before. We know that it has a hydrogen bonded to the oxygen, and that oxygen atom in the middle has 2 lone pairs of electrons, giving it 4 electron groups, an overall electron geometry of tetrahedral. But when we consider the molecular geometry, what we have is a bent arrangement. Very different from a linear geometry in that, of course, the angle between those 2 bonds are not 180 degrees. Okay, what is the angle of those bonds? Well, it turns out that they're going to closely mirror the bonds for a tetrahedral molecular geometry, such as the one we showed in methane, which has 109.5. But it turns out that the bonds are slightly lower, slightly less, because those lone pairs of electrons, which are not bonded to another atom, have a slightly higher repulsive force. So they sort of squeeze those bonded atoms together a little bit, decreasing the bond angle to 107 for ammonia, or the 2 lone pairs of electrons for oxygen push those atoms together to an angle of 104.5. Okay, so now what happens when we look at molecules with 2 or more central atoms? So far all we've looked at is 1 central atom and discussed its molecular geometry. Okay, well, it turns out that that's easy. All we're going to do is to take a look at the individual geometries of the central atoms one at a time, and that will determine the overall structure. So here we have the 3-dimensional structure for methanol. We've drawn the Lewis structure for this species. We know it looks like this. Okay, clean that up a little bit. We can see that this carbon atom has 4 electron groups. All 4 of them are bonded, so that will give us a tetrahedral geometry on the carbon atom. And we can see that the oxygen has 2 bonded atoms, 2 electron lone pairs, okay, for a tetrahedral electron geometry and a bent overall geometry. Okay, so summing these, this is what methanol looks like in 3 dimensions due to its individual geometries of its 2 central atoms.